Hey guys, thank you so much for joining in on this live session with Manifold AI Learning. So, team, the topic of today's session is discussion about the transformer architecture. So, welcome everyone on this live session. Now, this session is made possible with the team of Manifold AI Learning. So, my name is Nachiket Murthy. So, I've got an opportunity to publish multiple courses through Manifold AI Learning. So, Manifold AI Learning is an e-learning platform where you can access some of the top class courses on the field of data science, machine learning operations, AI ops, large language models, generative AI certification. So it's a one-stop destination for learning the trending technologies so that you can stay ahead in your career as well as on your curriculum, guys. Let me show you the link and I'll give you a few seconds. So as you can clearly see, Manifold AI Learning has got variety of courses that suits the individual preference and the requirement. There's a course on mastering the generative AI, which is a package which contains more than 14 courses that would help you to master the generative AI in 2024. And this is a growing package. That means any new releases that would happen in the generative AI space, which is getting released by Manifold AI Learning, you get the access for free. So this is like a single time investment for your generative AI. And this package, if I want to highlight some of the key things, so you'll get the course on NVIDIA certification, which is one of the trending certification that we have got right now from NVIDIA. And it includes Python programming for MLOps, prompt engineering and LLM ops course, where you'll be doing hands-on project with OpenAI as well as the Hugging Face, the generative AI bootcamp, where you will learn where you will master the natural language processing from scratch. And there is also other courses from Manifold AI Learning in the MLOps space. There's MLOps Bootcamp, which is one of the top selling course and which is being learned by more than 50,000 learners across the world. And there's another top course from Manifold AI Learning, that is MLOps with AWS. So do check out these courses from Manifold AI Learning. And for there's a limited offer that's going on Manifold AI Learning. You can check out the offer once you go to that page. So there's a 5% discount that's going on most of the courses. So you just have to click on join now and you'll be able to apply the discount and sign up on the Manifold AI Learning platform. So by joining in, you'll get the expert access, and you also get to be part of the Manifold AI Learning community. Get the personal invites, ensuring that you'll always be invited for any live session that are being conducted by Manifold AI Learning. Okay, so with that, we'll get started with today's agenda. See, the agenda of today's session is to decode the transformer architecture. Now, this transformer architecture is one of the important architecture, even though we have got a lot of generative AI and a lot of generative models in place, this still holds an important element in the generative AI learning journey. So considering its importance, we have added this live session so that most of you can benefit by understanding what is transformers architecture, why is it important, what is the importance of it, and everything we'll be learning as we progress in today's session. Now, before we get started with transformers, guys, I want to know from you. So, what's your understanding about the transformer architecture? So, let me know, guys. What's your understanding about this transformer architecture, and how do you describe this transformer architecture? So you can let me know in the comment section. Okay, I see response from Lakshman. It's a large language model. Okay, that's okay. Thank you, Lakshman. Okay, Diksha. Thank you, Diksha. How about others? What do you think? Do you have any existing knowledge of transformers? Thank you, Pooja. Pooja says it's a architecture which proposes to uh, process the sequence data. That's correct. Akshata says it's an architecture for working with NLP data. That's correct. How about others? What do you think about the transformer architecture? And Navi says that decoder only model. That's correct. So decoder only model, we can say it's one of the part of the transformer architecture. But at a very high level, the transformer is made up of both encoder and the decoder. Okay. And how about others? What do you understand from transformer architecture? Are you aware of it? That's great, guys. Okay, thank you so much, team, for confirming. So, as most of you have mentioned, so transformer architecture is is actually is actually a, we can say, one of the revolutionary approach that we have got, especially when it comes to working with the sequence data. So, when I say sequence data, one of the classic example that I give for the sequence data is the text data. So the reason, because here, when we are working and when we are reading any text, okay, as a person, let's say if I'm reading any book, if I'm reading any book, so let's say I have completed the page one. Now, when I move on to the page two, I'll not I'll not forget everything and I'll start from scratch. So I'll remember what has happened in the previous page, and then with that knowledge, I'll continue with the reading of the next sentences or in the next page. And it's true for even in the next word as well. So we have to remember what has occurred in the past. Now, the same thing is essential while working with the text data. If I want my machine learning model to understand what is happening inside this text data. Now, let's understand why traditional machine learning models cannot do this. Well, if we consider the traditional models, let's say the deep learning neural network, or the classic machine learning algorithm, what it treats is it is going to treat each row in our given data set as an independent element. So it's going to pick up first row. I'll just give an example. Let's say it will pick up first row. It will perform a forward pass. It will perform the backward pass. It will update the weights. Okay. And then it just picks up the second row. So whenever it is uh, performing these kind of transformation, it is just considering the features. It will perform the forward pass and backward pass. And even if you consider the individual elements or individual features that we have got, we are going to treat those individual features as like an independent one, and we would go ahead and perform this forward pass and the backward pass, and we will treat them independently. Now, suppose I've got a text like this, where the text says that dog is crossing the road. It is very tired. Now, if I ask you what exactly is this word it is referring to? So, as a human, it's very easy for us and it's natural to say that the word it is actually referring to the word dog. But if you want the computers to do the same thing, that's when the challenge arises. Most of the traditional algorithms that we have got do not have the capability to learn these kind of sequences in a given data set, and that's where it would struggle. So what researchers have proposed is, so they proposed an architecture which is a well-known architecture that's called as a recurrent neural network. Now, what is recurrent neural network? In the case of a recurrent neural network, you will have a recurrent connection. Let's say this is your xi, and whatever the uh, processing in the hidden data that you have got, let's say hi minus 1. So like while processing the input of your current state or in the current timestamp, when you're processing the input in the current timestamp, you'll also consider the hidden state from the previous neuron along with the current state, and you will generate the output. So here you can see that there is some kind of a recurrent connection that we have got right now. So by doing like this, we are able to remember the sequence because each time when I'm working with the recurrent neural network, I'll be processing one word at a time in a sequential manner. Suppose if my sentence has got 10 words, okay, if my sentence has got 10 words, then I'll be using 10 words in a sequence. I'll be providing this 10 words in a sequence as an input. And here I'll be processing that data. So that's what happens in the case of this recurrent neural network. Now, it was okay for the smaller sequences. It actually worked fine and it powered some of the greatest application that we were using at that time. Now, this recurrent neural network was powering the Google search engine. It was powering the various platform, especially when we had to deal with the text data like the applications such as machine translation. But soon we started facing the challenges with this recurrent neural network. The challenge that we faced was limited parallelization during the training. So, whenever you're working with this recurrent neural network, so one challenge that you would face is you have to pass the data in a sequence, one word after the another word. That means even though you may have a parallel processing GPU hardware, you still cannot make the best use of it because the architecture is not designed to do the parallelization. So that's a performance bottleneck. And another problem is when we are working with this recurrent neural network, it was unable to capture the long range dependencies. So if you have a lengthier sequences or lengthier sentence, that's when the recurrent neural network struggled. It could not remember the sentences over the long sequences. So that is the second challenge that we started facing. And since if we are processing in a sequential way, that means one after one word after the another, so even though we may have a powerful hardware, since it is not built for parallelization, so this leads to lower computation. So as a result of this, the training was slower. It was taking months together to perform the training to learn the patterns in that sequential data. And when it comes to inference, even like we were generating the output in a sequential way. Even we had that issues over there. So these were the challenges that we faced with this recurrent neural network at that time. Now researchers started proposing some solutions around it. They proposed alternative neural networks such as the LSTM neural network, that is long short-term memory neural network. Now with this long short-term memory, we were able to include the long-term memory as well as the short-term memory, but still we were facing the similar challenges, that is limited parallelization during the training, and we still had a challenge in remembering over the long range sequences. And obviously, we were having the slowness in the computation. So, this was a challenge we had with the sequence based architecture when we are working with the text data at that time. So, then what happened was in the 2017, a research paper was published by Vaswani et al. And they introduced a transformer architecture. And this became one of the revolutionary approach for the sequence processing task. So wherever we were struggling with the sequence tasks such as the machine translation or language modeling. When I say language modeling, it's a task where given a current word, you want to predict what is the next word. So this revolutionary approach has actually transformed the way in which we would work with this sequence data. So it brought in a lot of benefits for us. And here, just like we have had the encoder decoder architecture using the RNN, even this transformer architecture, it proposed the encoder decoder architecture. And some of the key features which are noteworthy, especially about this transformer architecture, are the self attention, multi head attention, positional encoding, and the encoder decoder. So these are the key features which made one of the popular choice, especially while working with the sequence data. Now with the self-attention feature, so this allowed each word in a sequence to understand its relationship with the other words that have got in the sequence, so that we can understand the meaning of a current word by looking at the other words that have got in the sequence. And we have the multi-head attention. So with the help of this multi-head attention, so multiple self-attention layers, they started to operate in parallel. So we have got this multiple self-attention layer which operates in parallel. Now each of this uh, head focus on the various aspects of the input sequence. So as a result of this, this helped us to learn the pattern between the words in a much efficient way, even if the sequence is lengthy. So that means this helped us with with solving the problem that we had with LSTM and RNN, that is remembering over the longer sequences with the help of the self attention and multi-head attention. So we were able to learn the relationship between the words in a much effective way. And this transformer architecture, it also introduced the ability to process the words in parallel. So previously I've mentioned that in case of RNN and LSTM, so we had a challenge where we had to where we had a challenge where we had to specifically like follow in a sequential way, like we had to sequentially process the data. So that was one of the key challenge that we had, where you had to process one word after the another. So that was one of the key challenge that we had with with this RNN approach, or that is the RNN and the LSTM approach. Now, what they have introduced is they have said that you can send in all the text together. That means the parallelization came into picture. Now, when parallelization is happening, so we still need a way to represent the position. To give you an example, suppose if I've got the text that says as man uh, eats dog. Okay, I'm just giving an example. So when I say man eats dog, it means something, and if dog eats man, it means something else, because the sequence in which the word is used in a sentence matters the most in the English language or in any language, as an example. So that means this, like, we want to have a parallelization ability. So when I say parallelization ability, I'm able to process all these words together. But how do we convey the information that, okay, man is the first word or man is the last word? And that's where this transformer architecture, they have introduced something known as the positional encoding. So with this positional encoding, so we were able to add the input, like we were able to specify the position for our input data, which ensured that even though we are processing the words in a sequential way, we are still able to provide an information to our model saying that, hey, this is my first word, this is my second word, this is the third word, and so on. And also, another best part about this transformer architecture is the encoder decoder. So this transformer uses the encoder to process the input sequence, and then it will also use the decoder to generate the output sequence. So it uses both the encoder and decoder. So, and the best part is both of these, encoder and the decoder, both of these consist of the self attention and the feed forward layers. So with these key features which were introduced, this makes it this actually resulted in one of the important transformer architecture that we have got these days. Now, once this was proposed, once this was proposed, various large language model capabilities and versions were introduced. But before we talk about, yes, so if I want to give some additional information about the various components, so first thing that I had mentioned was positional encoding. So here, since the transformers doesn't have the built-in way to understand the sequence or the order in which the words are being present, so these positional encoding provides a way to inject such information about the relative positions of the word in a given sequence. Unlike RNNs, so these transformers have got an ability to process all these words in parallel without the inherent knowledge of their order. So, as a result of this, this can make it difficult for accurately capturing the meaning because the word order is crucial in the language, and that's where the positional encoding would come into picture. Now, these positional encoding, what it represents is it represents the unique vectors. Now, each word position in a given sequence is assigned to a vector, which we also call it as the positional embedding. So we will have some kind of a positional embedding. Let's say this is a specific word that I've got, and for this word, this is my word representation in a vector format. We call it as the word embedding. And along with that, we'll also have the positional embedding as well. Okay, we'll also have a positional embedding which represents the vector which represents the position of a vector. And what we do is we are once we have got the positional embedding generated for an individual word, we are going to add it to our word embedding, which means we are going to infuse them with the information about their position with the sentence. And that's what we call it as the positional encoding. Now, here, when it comes to positional encoding, to give you some technical details around it. So, here in the case of positional encoding, so these positional encodings are calculated using the sine and cosine function. So, as a result of this, this would produce a pattern which conveys the position information. And then, as I mentioned, we'll perform the addition. So whatever the positional encodings that we generate, we are going to perform the element-wise addition to the word embeddings, which is like injecting the position information to the word embedding. Now, here in the formula, if you observe, when it comes to generation of this positional encoding, okay, so here we are making use of the sine and the cosine function. So the reason that we are using the sine and cosine function, because the sine and cosine function allows our model to easily learn the relative position of the words. So if we make use of the traditional approach, let's say normalized values approach in the case of positional encoding instead of sine and cosine, the challenge that we are going to face is if the sequence is very large, that means if you have a lengthier sequence, the normalized value will be very small. And if the sequence is very small, the normalized value will be very high. So which is going to cause confusion when we are injecting that positional information to our word embedding. So that is the reason we prefer to use this sine and cosine model. Now with the once we generate the positional encoding, so this is a visual representation of the positional encoding. So to have a quick recap, what we have learned is that whenever we are working with the transformer architecture, we have something called as positional embedding. So what happens is in that step, we are going to generate the positional encoding using sine and cosine functions. And we will have an input. And for the input data is nothing but a specific word, an individual word. For that individual word, we are going to generate a vector representation with the help of word embeddings. We call it as the input embeddings. And we will add our word embeddings to our positional encoding. So as a result of this, we are going to have the position data fused to our word embedding, which is the numerical representation of the text data. Okay, that is the overall idea behind this positional embedding that we have got as part of this transformer architecture. So team, is it clear so far? The intuition behind this, the positional encoding, is it clear so far, folks? If yes, please confirm. Thank you, Lakshman. Thank you, Dheeraj. How about others? Okay, thank you, Shruti. Thank you, Kavya. Thank you, Josie. Thank you, Sangeeta. Okay, that's great, team. So, thank you for confirming. So, let's proceed ahead. So, you have learned about the positional encoding and the importance of it. Now, let's take a look into the next important element of this transformer architecture, that is the self attention. Let's understand about this self attention component. In the case of this self attention component, so what happens is, uh, okay, so here before I go over there, I see a question from Sauhardya Das saying that how do we generate the embeddings at the first step? Okay, that's a good question. So here we will make use of pre-trained word embeddings. So there are various word embeddings option that we have got, and one famous word embeddings is word to vec model. Okay, there is already a pre-trained model where a word to vec model that we have got. Now, what happens is this word to vec model has been trained on a large corpus where it was trained such that given my current word, it has to predict the next word. That means it has to go ahead and tell us, it has to understand, okay, what would be its surrounding words. So at the end, what we would have is, as an outcome of this word to vec model training, we will have the information about if my particular word is present, so how exactly it has to be represented in a vector space, so that the words which are having the similar context will be having a same vector values. Okay, that's the core idea behind this word embeddings. So we will make use of such word embeddings, like such pre-trained models embeddings, and you send in our data and get the word embeddings values. So to specifically illustrate this, think of it in this manner. So let's say I've got the text that says as dog is crossing the road. Okay, let's try to break this down so that everyone can get an understanding as what would happen. The first thing that we would do is we will do the tokenization. That means we will split our sentence into the individual tokens, which can be processed by my model. Dog is crossing the road. Okay, I'll be splitting my entire sentence that we have got into the individual tokens so that it is easier for us to process. Now, I cannot use the text data as it is. So since we cannot use the text data, what we have decided is we will make use of the pre-trained embeddings model. So I'll make use of word to vec model, and using that word to vec model, I'm going to generate the vector representation of this individual word. Okay, so if I do that representation, let us assume that this is a vector representation of the word dog. Like I'll have some dummy values just for the understanding. I'll say 12, okay, 15, -2, 8. So it means I have some vector which is represented in 4 dimension, and the values in 4 dimension are 12, 15, -2, and 8, which means this dog word can be represented as a vector in 4 dimensional space, where in each dimension, this is the coordinate value. Okay, that is what we have got. And to generate this word embeddings that we have got, that is input embedding that you see, I'll make use of the word embeddings model. Like an example, word to vec. So why did I come up with this vector representation? See, I need the data in a numerical format. Without that, I cannot process it with the help of deep learning models. That's one thing. And with the instead of simply coming up with the values like numerical values, okay, instead of simply coming up with the numerical values which doesn't remember what is happening or which doesn't consider what is happening over there, especially in the especially the words in the sequences. Word embeddings makes more sense because this model has been already trained such that the words which are having the similar context will have a similar vector representation. So that is the intuition behind this word embeddings. So we'll be doing the same thing for each and every word that you see right here. That's the step that we are talking about. Okay, so for each word, obviously the vector representation will be different. Maybe this will have different coordinate. So this is one vector. Unlike this, I'll have another vector and so on and so forth. Okay, that's the overall idea of this word embedding. So here word embedding is nothing but generating the vector representation for the individual words. So that's the core idea about this word embeddings model. Now, once we have this word embeddings, now what we are seeing is, okay, we will make use of cosine and sine positional encodings. Like I'll just give you a random example. Okay, just for our illustration, I'll show you so that it is much simpler for you to build the intuition. So you don't have to worry about mathematical formula, at least as of now. For now, just build the intuition around it. Let's say by considering these four values that I've got in this each vector, okay, and I have, let's say, four words in this in five words that I've got in this given sequence. Okay, so what I'm going to do is I'll apply the cosine and the sine function, and here I have come up with the positional encodings like this. So let's consider the positional encodings as 0.15, 0.2, uh, so let's say a point 0.3, okay, and then let us assume this is zero point 0.4, or let's keep it as zero point 0.1 only. So this is my positional encoding. This is my positional encoding, which I've got as an output by applying the sine and the cosine function. Okay, that is what the positional encoding is. Now, what we are seeing is we are going to add, okay, whatever the positional encodings that we have generated, we are going to add it with our word embeddings. We will add it with our word embeddings. And here, this would result in a vector format where I'll have the overall output this time as 12.15, 15.02, 15.2, and this is minus 1.7, 8.1. So this is the overall output that I would get after I apply my positional encoding to my word embedding. So that is what the symbol over here plus represents. So here, if you have observed in this example, okay, if you observe in this example, I'll have an input embedding. We have an positional encoding. There's a plus symbol over here, which represents that we are going to perform the addition. Okay, so that's the idea about this, the positional encoding, which we included for our input embedding. Now, once that is done, so we also have another functionality that we have got inside this transformer architecture that's called as the self attention. So this self attention will help us to understand, okay, how much importance that I have to give for the other words when I'm processing my current word. So that is the overall summary that we can say when we are working with this self attention layer. So what happens is in the case of the self attention, so we will have each word is going to create the query key and value vector, and then we are going to uh, we are going to make use of this query and key vectors, and they are compared to compute the attention scores, and these attention scores are basically used to weigh the value vectors, and this will produce the weighted representation of the overall word's context, which says if I'm processing my current word, how much importance that I have to give for the surrounding word so that we can understand the overall context. Okay, that is the overall idea about the self attention. And here in this transformer architecture, you will also come up with what we call it as the multi-head attention. So which means we will have multiple such self-attention so that we'll be able to learn the relationship between the words in a much detailed manner. So that's the idea about this self-attention. Okay, so I'll take a pause here. So we have looked into the introduction of self-attention, and we have also looked into the explanation of the positional encoding. So team, are we good so far? So are you able to follow along till now? Please confirm. Okay, thank you, Dheeraj. Thank you, Rakshit. How about others? Thank you, Shruti. Thank you, so Soumya. Okay, great. Thank you so much, guys. Okay, thank you, Yash. Perfect. So what you have now understood is you have understood how the data will be processed. Okay, just a second. Yeah, what we have understood is how the data will be processed inside our network that we have got. Okay, and especially how to positional encoding would work, and we have also seen as how self attention would work. Now let's go ahead and let's look into some of the key terms as well, especially on this self attention, and let's try to understand how does this self attention would work. Okay, so let's take a look into that same. Okay, now that you have an overall idea, so let's try to understand this overall architecture of these transformers in detail. So to understand this, let me open up my OneNote and we'll type and we'll try to understand it in a detailed manner about this transformers. So this is how a transformer architecture would look like. Now, when we talk about this transformer architecture, you have looked into the important components of this transformer architecture. You have looked into the self-attention, you have looked into the positional encoding, and how does the word embeddings will be injected to the positional encoding. And then we have learned that, okay, we have something called as the self-attention that that would enable us to learn the relationship between the words in a better way. Now, before we dive deep, so let's take a look into at a very high level when we talk about this transformer architecture. Now, when we say transformer architecture, it's also known as the encoder decoder architecture. So what this transformer contains is it consists of series of encoders where it will accept the input data and process it using the multiple encoders, and the output from the encoder is used as an input for our decoder. Okay, that's the idea behind this encoder decoder architecture. Now, each encoder that we would consider, okay, so this right here, this right here describes the individual encoder. Okay, each encoder that we have got right here, it has got two components. One is self attention component, and the other component is actually called as the feed forward neural network architecture, or the feed forward neural network component. These are the two components that we would get to see in the case of this encoders. Okay, we'll have a self attention, and this self attention is followed by the feed forward. Okay, feed forward neural network, that is what we have got. And I'll have multiple such encoders where I'll be stacking one next to each other. And and what I'm saying is, once the final encoder is present, from that final encoder we'll send that as an input for the individual decoder. So this is how the overall connection would exist. Now, what we have understood when we are working with the data, so here we will have the word to vector representation, that is word is represented in a vector format. Then we are going to inject its position with the help of the positional encoding, and we will have a vector representation of an individual word where it also consists of its relative position as well. Now, this representation of the words that we have got, this will be first sent to a layer which we call it as the self attention layer. Okay, it will be sent to this self attention layer. Now, this is one of the important property of this transformer architecture. Okay. Now, whatever the output that I would get from the self attention, let's say I'll call it as Z. Okay. The output from this self attention, this is obviously resulting in another vector itself. So this is another vector itself. So what we would go ahead is, we will send this vector, whatever that we have got from the self attention layer, to our feed forward neural network. Okay, so this is how the data would look like. Now, obviously, from this feed forward neural network, when the data gets processed from this feed forward neural network, we'll also get another output. Maybe I'll call this output from this feed forward neural network as, let's say, F1. So that's the overall way in which we would process the data. So the encoder that we have got, it receives the vector representation of our input word, where it also contains the relative position in my given word, and then it process it first with self attention layer, which is then followed by the feed forward neural network layer. And finally, once this is completed, then once the output from this feed forward neural network is completed, it would then go ahead and send it to the next encoder. So that's the general idea about the data in which it would flow. Now here we have something called as a self attention layer. So let's try to understand what is the self attention layer. So this self attention layer will help us to understand how the relationship between my words would look like. So that's the overall idea about this self attention. Now, to help us to decide how one word uh, uh, is important to the other words in my given sentences, so what we will do is, here we'll create three vectors from the encoder's input. So whatever the input that we have got for a given data, we are going to generate, okay, we will generate three vectors from this. So for the demonstration purpose, I'll be mentioning in this format. Let's say this is one vector, which we call it as Q. There's another vector that I'll call it as K, and the another vector, which we can call it as V. Query, key, and value. These are the three uh, unique vectors that we have got. Okay, these are the three unique vectors that we are going to generate from the encoder's input. Okay, so for each word that we have got, we will have three words. We'll create a query vector, key vector, and the value vector. Now, once we have these vectors, now these vectors are then created by multiplying the embedding by three matrices that we have trained upon. So that means I'll take a dot product between my uh, given data with Q. I'll take a dot product between my given data and K, and I'll take a dot product between the given data and V. Okay, we'll consider those, and once we have those in place, okay, once we have those, that is Q, K, and V in place, then we can go ahead and perform the operation. So what we are going to do is, in this scenario, once we have this Q, K, and V, okay, we are going to have, okay, at uh, like each and every word that like in general, what would happen is, so this Q, K, and V will be generating as a matrix. Will generate it as a matrix. So whatever the data that we would have, let's say x1, x2, x3, which is nothing but my individual words. So I'll take a dot product between my input and the respective q, k, and v. That is wq, wk, and wv. That is weight q, weight query, weight key, and weight values. Then I would come up and generate three new vectors, which we would call it as q, k, and v. So since it's a first data, I'll call it as q1, k1, and v1. Okay, this is what we would call it. And similarly, we will have the q2, k2, v2. So q3, k3, q3, k3, and v3, and so on. So like this, we would go ahead and generate the entries over here. Okay. Now, once we have these query, key, and value vectors, okay, the next step that we will do is we will have to calculate the score. So this score is important. That would help us to determine how one word is related to the other word, or how important the other words that I've got in my given sentence, given my current word. So we will go ahead and find the values. So in order to find the value, what we will do is we'll multiply q and k. Okay, we'll multiply q and k, and after we multiply this q and k, so the strategy that we follow is, suppose if I want to calculate the weightage that I have to give for my other words when I'm processing my current word, that is word 1, then it will be given by q1 k1, q1 k2, q1 k3, and so on. Okay, from this we will come up with the score, and once we come up with the score, we will divide it by the dimension of k, that is square root of dimension of k. And whatever the output that we would get, we will use that output, and finally we will apply the softmax. By applying the softmax, we'll be getting everything in the probability scores. So that is what it would happen in the backend. Now once we have the probability scores present, then we would go ahead and uh, like that once we have this probability scores present, then we will go ahead and perform this activity, guys. So we'll, once we have the softmax, so whatever the softmax output that we would get, we'll multiply it with v values. So this is going to help me to scale the values of v. If the values of this probability softmax is 0 or closer to 0, that means that particular word do not have impact on my structured sentence. Okay, that is what it would mean right here. And then once we have it, so we are going to consider those weightage as well. Then we will have the values of Z1, that is nothing but the outcome of Q, K, and V. So that's the idea about this self-attention model. Now, what I've just explained is a single self-attention model. Now, in reality, while working, so we will have multiple such self-attention. We also call it as multi-head attention. So in this case, it's still the same, but instead of using the vector approach, we'll be using the matrix approach. That is the only difference that we can say compared to the steps that we have just understood. Now, once we have it, we'll have the attention head, and then we would go ahead and process the output from this encoder. Now, this output from this encoder is will be uh, like sent as an input for the decoder. And when it is working with the decoder, there are few aspects that you need to remember is in the case of this decoder, we have something called as masked multi-head attention. So this will help us to remove the biasness that we would get if we have multiple training examples. Okay. And also it would this like this a decoder that we have got, it also does one more thing. It will also help us to uh, what it does is this decoders, it will also like remember. So the reason that you see it as masked because it is going to make the values for the future words to be negative infinity. So that's what it does, and as a result of this it would be ignored. So when the decoder is performing and generating the text, it will not be able to look into the training data with future data, that is future values. So that's another thing that you need to remember when we are talking about this decoder architecture. And inside this self-attention and feed-forward neural network, we'll also have some add-on normalized layer. We also have the concatenation and the residual connection to overall complete the connection of this transformer architecture. Okay, that is the overall idea right here. Now there's a question over here I see from the chat window. So Sauhardia says that is the output from encoder of step 0 is one of the inputs of the step 1. Okay. No, no, Sauhardia. So here, what happens is, okay, if I have 4 words, or let's say if I have 5 words that you would see right here in a given sequences, I'll be sending all these words together. Now, at this point in the self-attention layer, since I'll be multiplying the Q and K with the other values of K, so we'll still be able to look into the other words. But when I'm sending the data, I'll be sending it together. Okay, that is the overall idea as what is happening in the backend. Okay, now here when we talk about this uh, transformer architecture, there are various kinds of transformer architecture. We have encoder only model, we have decoder only model, and uh, uh, we also have the encoder decoder model as well. Okay, that is also what we have got uh, over here whenever we are working. Okay, so that's the idea about this transformer model, guys. I'm just checking if you have the additional information. Okay, now when we talk about, as I mentioned, we have got various types of models, right? So we have the encoder only model, we have decoder only model. If I want to give some example, so under this encoder only model, if when we talk about the encoder only model, so here it will have the only the encoder component of this encoder decoder architecture. And one of the classic example is BERT. And when we talk about the decoder, so under the decoder or only model, it is generally used in GPT based model. This is extremely good in generating the content. So that's where you would see the usage of decoder. And we also have the encoder decoder. So these models combine the encoder and decoder components of this transformer architecture so that it can understand the given data and also generate the content. Okay, so these are all the various types of the uh, large language models that you would generally come across, which are based on this transformer architecture. Okay, so that means the advanced transformers that we would see these days are actually based on the like advanced generative AI models are based on these transformer architecture. All right, guys, I highly recommend you to learn more. If this sounds interesting, I highly recommend you to uh, refer to the research paper of Attention is All You Need so that you can get a deeper understanding of this transformer architecture paper. Now, if you're someone who wants to dive deep into this natural language processing and understand how to work with the text data, I highly recommend you to check out the courses from Manifold AI Learning. So you can definitely check out the course on generative AI natural language processing bootcamp. That would basically help you to master the natural language processing. And if you're someone who wants to ensure that you master everything that is required for in the generative AI space, do check out one of the premium package that is there from Manifold AI Learning, that is Generative AI 2024. And the early learners who are joining in today, you'll also get the additional 5% off on the prices that you see on our website. And if you have got any questions, guys, do post your queries in that chat window. So, like we have people from the admission team, and they'll be able to help you in case if you have got any questions. So, with this, folks, we come to the end of today's session. Okay. So, like, thank you so much, everyone, for taking your time and joining in today and interacting with me throughout the session. So I appreciate you joining with us, and I appreciate you taking time and asking some of the amazing questions throughout the session. So as I mentioned, if you do not have any further queries, and like if you do not have any further queries, yes, you can feel free to drop. The session's recording will be made available on the Manifold AI Learning courses. There is something called as Manifold AI Learning workshops. The recordings will be made available to you here. So ensure that you enroll to the Manifold AI Learning portal and access this session's recording. You can also have the session's recording of previous sessions as well. Okay. So thank you, guys. So if you've got any question, please let me know. If you're clear, please confirm by typing in as all good. And I look forward to seeing you next time. Okay, I see a question right here. Josie says that what is BERT generally used for? Okay, so here when we talk about the BERT, so we generally use this for it. We call it as the encoder only models. So we generally use it for understanding uh, uh, like uh, uh, like understanding the sequence data. That's when we actually make use of this BERT language model. So the tasks such as name identity recognition, question answering, text classification, machine translation. So those are all some of the common tasks that we do it with the BERT large language model. So Navi says, will the premium course cover all the courses on the website? So here, this covers all the courses which are in the domain of generative AI. So there are MLOps course. MLOps is a separate package. You can also check out the scheme. But everything from the generative AI space is covered here, like which includes the NVIDIA certification, which is one of the upcoming like latest certification in the generative AI space from the NVIDIA. You get to get the learning materials around it, the Python programming, the Python for data science, NLP basics, LLM ops, the deep learning with TensorFlow and PyTorch, machine learning certification so that you can apply the machine learning and deep learning on cloud, the mathematics for machine learning, deep learning, which includes linear algebra, statistics, and calculus, all the essentials that is required for the learner to master the generative AI is part of this package. For someone who wants to master the MLOps, you can check out the machine learning operations package, which includes the courses which are relevant for the machine learning operation. There's an MLOps bootcamp and the MLOps with AWS and the content which is related to that. You can check out both the packages. Okay, thank you, Navi. Okay, any other questions, team? Thank you, Josie. Okay, Rakshita says, can I join? So, Rakshita. Okay, any other questions, team? Thank you again, guys. Okay, I just got to just one more thing, guys. I think I got a note from the admission team. There's only a few vouchers left in the early discount option. If you're someone who's planning to sign up, so make the most of the offer that is running in. Okay, thank you so much again, guys. And I look forward to seeing you next time. I'll be just be there on silent for another minute. If there is no further questions, I'll be ending the session. So thanks again, everyone, and I'll see you next time. Thanks all. I'll be closing the session.